Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will find the maximum volume of a shape when given its surface area. So in this question, the shape is a cylinder. So we're told its surface area is 200 centimeters squared and we want to find its maximum volume. So whenever you see maximum or minimum, I want you to straight away think of optimization. We find the first derivative and find where the first derivative equals 0. So because we're talking about the maximum volume, we're going to use the volume formula for a cylinder, which is this one here. So there's a problem. This formula has two unknowns. Two variables R and H. We don't know how to solve optimization problems. We don't even know how to differentiate functions when there are two unknowns. So I'm going to have to use a bit of trickery here. The first thing I'm going to need to do is write H in terms of R. So what does that actually mean? That means I want an equation where H is the subject and it equals something in terms of R. It has an R in it. So why do I want that? Well, I can then use that to substitute back into here for H, so I can write the volume so it only has R's in the equation. Then I'll be able to differentiate it. So how am I going to get such an equation? Well, I'm going to use the fact that the surface area is 200 centimeters cubed. So I have surface area, which is 2 pi r squared plus 2 pi r h is equal to 200. So what I need to do is rearrange this so that H is the subject. Now, it might look complicated, but it's actually really simple. It'd be really hard to make R the subject because it's in two spots, but making H the subject won't be too difficult. So we have two terms. This one doesn't depend on H. It has no H's in it. This one does depend on H. So I can get rid of this first term that doesn't depend on H by simply subtracting it from both sides. So I'm going to start off by minusing 2 pi r squared from both sides. So that will simply give me 2 pi r h equals 200 minus 2 pi r squared. So now how am I going to get H by itself? Well, I've got something times H. You know, this is just the steps of solving equations that you've done since year 7. You know the way I undo timesing by something is to divide each side by that something. So I'm simply going to divide each side by 2 pi r. So if I divide the left-hand side by 2 pi r, I'm left just with H. For the right-hand side, to divide by 2 pi r, I need to divide everything by 2 pi r. So I need to divide 200 by 2 pi r, and then I need to divide 2 pi r squared by 2 pi r. So I can simplify this. It simplifies nicely. So 200 over 2 is just 100. So this first term is just 100 over pi r. And the second one simplifies nicely. I can cancel the 2 pi's. R squared divided by r is just r. So I've written an equation of H in terms of R. So I can now substitute that back in and I'll now be able to differentiate. So substituting this into my volume equation, I have volume equals pi r squared h, but I just found that I can replace h with the equation at the bottom. I can replace it with 100 over pi r minus r. So we're just going to expand this to make it easier to work with. So if I go pi r squared times 100 over pi r, the 2 pi's cancel out. So I have r squared divided by r. Well, that's again just r. So this first term is 100r. That's what I get when I multiply this and this. So multiplying pi r squared by negative r, I just get minus pi r cubed. So now I have a function for volume that only has one unknown, which is the r's. So now I can simply differentiate and find where it equals 0. So the derivative of 100r is just 100. The derivative of pi r cubed, move the power to the front and decrease the power by 1. So to find where this function here is maximized, I need to find where the first derivative equals 0. So if I have 100 minus 3 pi r squared equals 0, well, that just gives me 3 pi r squared equals 100. Solving for r, I divide each side by 3 pi. And then to undo squaring, of course, you know it's square root. So r is the square root of 100 over 3 pi, which is about 3.26. Now, r is in centimeters because the surface area was given in centimeters. So what have I actually found? I've found that the volume will be maximized when the radius is 3.26 centimeters. So just note, when I square root something like this, there is a positive and a negative solution, but I don't need the negative solution here because I'm talking about a length, the radius. So we only take the positive solution of r equals 3.26. The maximum volume, to find that, I just substitute in 3.26 into this equation here. So then I get volume is approximately 217 centimeters cubed. So again, that number just comes from substituting this number into this formula here. So we have actually answered the question, but we might wonder, how do we know it's a maximum? Well, firstly, we know this can't be a minimum, because if you're asked about, minimum or maximum volume, the minimum volume would be 0. You can't have less than 0 volume. So that's one reason we know it's a maximum, but there is a more formal way to test this. And that is, of course, to use the second derivative test. So what I'm going to do now is simply differentiate the first derivative. So the second derivative of volume will just be minus 6 pi r. So that is just moving the power to the front and decreasing the power by 1. So remember, if the second derivative is greater than 0 at your stationary value, at your maximum or minimum value, that implies that the value minimizes the function. Whereas if the second derivative is negative, it maximizes the function. So if I substitute into this formula here, r equals 3.26, the volume would be minus 6 pi times positive 3.26. That is, of course, negative. So because when I substitute in this value, it makes the second derivative negative, that means that this is a maximum. I have confirmed and shown this volume here is a maximum and not a minimum. All right, thank you so much for tuning into this video. Best of luck for your exam, but you'll be fine. You're a superstar. This has been the luckiest maths teacher in the world. Have a great day.